So what we start with is this noisy image, which is going to be denoted by a vector y with an entry for each pixel. Right, so they'll all be zeros and ones, and we want to kind of invert this to get back to the original image without noise. Right, so this is an almost an inferential problem where our parameter now is the true image, right? So it's quite high dimensional. So if we think of this situation where we have 366 row pixels, 270 column pixels, capital N is of the order of maybe 99,000 or something like that, and well, that's a very, very large parameter, right? So how we're going to attack this problem is we're going to frame it as a hidden Markov model where the true image is the hidden Markov part and the noisy image is the observation. So we're trying to infer this underlying Markov random field. Now there are a few things that we're going to assume. So first of all, we're going to assume that theta is known. So theta was the probability of flipping any pixel. So the pixels were flipped independently. So by assuming theta known, and we're also going to assume that we know the noise generating process, then that makes our problem slightly easier. Okay, it's one less thing to worry about. Okay, and so the idea is to work backwards, right? So we're given y and we want to figure out what x is. And the way we're going to do that is we're going to first assume that x follows some kind of joint distribution, and that's going to what we call a prior. And then we're going to condition on y and look at the distribution of x when we've conditioned on y, right? So when we look at the noisy image. And what's also going to be involved in that conditioning is the noise generating process. After we've done that conditioning, what we do is we look at the distribution of the x's, right, the joint distribution, and we're going to sample from them using this kind of Gibbs sampling algorithm that we've used previously, but with a slight modification, as we'll see. And that slight modification involves bringing the observed image or the noisy image into the sampling, and also the value of theta, so the noise generating process. So this general approach, so BSAG talks about it a lot in his paper on the analysis of dirty pictures, which I spoke about even on the first day of this module, and it's kind of like we have this kind of inverse problem, right? So we don't know what x is, we want to know what it is, we assume it has some distribution, then we condition on what we've seen and figure out what the distribution of x looks like when that conditioning has been done. And in Bayesian terminology, this is called, so the initial distribution we assume on the unknown kind of true image is called the prior, and the conditioned distribution, so when we've conditioned on the noisy image and the theta, that's called the posterior. So what we're doing here is we're sampling from the posterior of the true image, and that's what we're going to be working towards. Now, so what components do we need to do this? Well, the first part of the recipe is to think about how x is going to be distributed before we've conditioned on y. And as we're framing this in terms of a Markov random field problem, and we have binary, so 1, 0 values at each of our pixels, it makes sense to frame x or to assume for x an autologistic model, right? Because an autologistic model, it's a multivariate structure where we have binary values at each of the sites, so 0 and 1, and then we can get this clustering with certain choices of parameters in the autologistic model. And what will that clustering do for us in this situation? Well, the clustering will allow us to obtain the outline of the cat, and also to obtain a clear kind of clear parts in the borders and on the internal part of the cat as well. So the clustering course means that if my value is 1, then I'm more likely to have neighbors with values that are 1 also. Then for y, well, how do we get from x to y? We can write down the distribution of a pixel. conditional on if we knew what the true value of the pixel was. So this is very like the top level of a hidden Markov model, where we have y given x. Y's are independently distributed given the x's, and of course theta will come into that. Okay, so let's just begin by writing down the prior for x. And that's going to be our trusty, our best friend now, because we've seen them so many times. This auto-logistic model, where we have two parameters, alpha and beta. We're going to constrain them. We'll talk about that a little bit later. So we have a sum over the single pixel values, and then a sum over all pixels and the pixels' neighbors. And as we saw previously, this will give us clustering in a spatial setting. Now, if we knew x, how would we generate y? Okay, well, how we do this is, well, we take account of the fact that the noise is generated independently at each pixel, and the pixel is a flip with probability 0.1. So we can write down the probabilities of combinations of x and y values. So we'll just think about a pixel, a particular pixel yi, and given that xi is equal to 0, well, that would happen with if the pixel if pixel I wasn't flipped, right? So that would happen with probability 1 minus theta, and then we'd have yi equal to 1 given xi is equal to 1. Also, if the pixel wasn't flipped, and then we have the remaining two where the pixel is flipped, right? So we have yi equal to 0, but xi was actually equal to 1, and that would happen with probability theta. And similarly, we have yi equal to 1 given xi equal to 0, and that would happen with probability theta. And what this allows us to do now is to write down the conditional distribution for a given pixel yi of the noisy image, given that we know the value of the true image. Now, so what we want to do is that when x and y are the same as each other, we want to pick up a probability of 1 minus theta. And when x and y are different from each other, we want to pick up a probability of theta. So let's just think about how we might express x and y having the same value. Well, we know that if x and y are both equal to 1, then xi yi will be equal to 1. And if they're both equal to 0, then 1 minus xi will be equal to 1, 1 minus yi will be equal to 1, so we'll get 1 there. And if they're different at all, then well, what's going to happen? Well, in this case, okay, if either of these are 1, we'll get a 0. If either of these are 0, we'll get a 0. Right, so having either of these situations, we define, say, zi as xi yi plus 1 minus xi 1 minus yi. Then if xi and y are equal, exactly one of these terms is going to be equal to 1. So zi can serve as an indicator for yi and xi being equal to each other. All right. So then, given that, what we can do is we can write down the probability mass function for yi conditional on xi and theta, which we're assuming that we know. And that's going to be, okay, well, if yi is equal to xi, that's going to happen with probability 1 minus theta, and that will happen when zi is equal to 1. And otherwise yi is not equal to xi, right? So the pixel is flipped. That happens with probability theta, and that'll be indicated by 1 minus zi. And then because the pixels are flipped independently of each other, then that allows me to write down the joint for y for the entire noisy image, conditional on the true image. And appealing to this independence of flipping over pixels, I can write down the joint distribution of yi conditional on knowing the true image as the product over the pixels in the noisy image. Okay, so that'll be 1 minus theta zi theta to the 1 minus zi. Okay, now so we have a prior for the true image, which we don't know, and then we have a likelihood for the noisy image conditional on the true image, right? And this should, so all the time here you should be thinking about these hidden Markov models in time, which we studied way back in chapter 2, right? Because there's a lot of similarities here. Now, the only problem here is, of course, we can't do the EM algorithm, right? So that's why we have to really think about how we're doing the estimation. And why can we not do the EM algorithm? Well, I'll leave that for you to figure out yourself. Okay, so if you write down the completed likelihood, you try and take some expectations, you'll sort of see fairly quickly why. Okay, so now, okay, so what we want to do is we really want the conditional distribution of the true image given the noisy image, right? And the other information that we have about the noise generating process, right? Which is actually essential, right? It's essential to know that. Okay, and that's going to be equal to the joint of y and x. So make reference here to the completed likelihood that we saw in chapter 2, divided by the distribution of y having marginalized over all of the x's. This thing on the bottom line is this formidable kind of marginal likelihood partition function style thing that we've seen cropping up a number of times throughout the module. And okay, well, this thing on the bottom here, we're looking for a joint density or joint mass function x. So this thing on the bottom here doesn't contain any x's, so we can filter it out using a proportionality sign. And what we're left with is this joint of y with x. The joint of y with x. Well, if we think about writing the conditional probability the other way around, we could write this in terms of a y given x and a marginal for x, right, which would be our prior. So what we could do is we could say, okay, well, this is actually the same as saying the probability of y given x times the marginal of x, right? So just kind of in flipping the order here on this side. And what that leaves us then is it leaves us with two things that we actually know, right? Because we know what p of x is, well, up to a constant proportionality. We know what this likelihood is here, conditional of y given x, because we've assumed that we know what the noise generating mechanism is. So these are potentially two things that we can get a handle on. Now we don't know p of x exactly, but we can write it up to proportionality, and so what this tells us then is that the conditional of x, the conditional of the true image given the noisy image, is proportional to a product over all pixels of the likelihood that pixel I is flipped multiply by this this autologistic model. Okay, so now we have a form for x, and really what we want to do is, well, ultimately we want to estimate x, but it's not going to be possible. So what we can do is we can try and sample x in a sampling scheme. Just noticed here a small little mistake, right? So that should be 1 minus zi there, which indicates that the pixel has flipped. So we can sample this in a sampling scheme, and that's what we're going to describe in the next video. So whenever you're ready, go over there